The speaker was supposed to be Professor Bertozzi, but for personal reasons, the talk has been switched to another day. And one would talk about Wasserstein network about gradient penalty.
Thank you for introduction, and then thank you for organizing this nice workshop, and thank you also for inviting me. So today I will introduce my recent work focusing on application. So I will explain how to train Wasserstein Generative Adversarial Network, briefly introduced by Augusto, without gradient penalties. So this is joint work with Guido Montefort at UCLA and Max Planck Institute and Yeon Kim and Insun Yang at Seoul National University. Okay, so here is today's outline. So I will briefly again introduce Wasserstein Generative Adversarial Networks, and I will briefly talk about some literatures. And then I will introduce our comparison-based training algorithm. And then I will give you some experiment and then some remarks as well as ongoing works. All right. So yeah, thanks to Augusto, I can briefly explain these generative adversarial networks, GANs. So these networks have been remarkably successful in generating synthetic images. So in the original model by Goodfellow et al., so we have two networks, the generator and then also discriminator. They compete each other. So we are solving the following minimax problem. And the original model, this V is given as follows. So more precisely, we have given real images, okay? So given real images, and then we also have n-dimensional noise vector. And if we consider like after push forwarding this noise vector to generator, we will get generated image, and then discriminator can tell if this image is real or fake. So this is the basic idea of GANs. And the Wasserstein GAN, the red part here, the maximum over discriminator D, is the Wasserstein distance. So more precisely, our training objective here is the Wasserstein distance to the target distribution. So formally, the main objective of Wasserstein GAN can be understood as follows. So we have two constants, m and n. M is less than or equal to n. And then we have two distributions. So mu is a target distribution, and then here rho is a source distribution. So like for instance, mu can be understood as a distribution of real images, and then rho can be understood as a noise distribution like Gaussian distribution. Then our goal is the following: to find a parameterized generator G so that Wasserstein distance between mu and then G push forward rho is close to 0. So as you may know well, computing the Wasserstein distance has been a difficult task. So there are a lot of related works, including the ones in audience, online, and also here. And I'm sorry that I couldn't include all the works, but yeah, let me also say that it's my great honor to speak in front of you. So the popular works is in neural network is, as Augusto explained, the synchronous distance. So first of all, this algorithm is faster than computing the Wasserstein distance, the actual Wasserstein distance. So it is, I would say it is useful in machine learning. And also the last work by Matt here and also Flavian. And in this work, they use contribution potential to compute the Wasserstein distance between, sorry, I should say the contribution duality formulation to compute the Wasserstein distance between two measures. And there are much more works regarding this. Okay, so since computing the Wasserstein distance is a difficult task, so instead of that, if P is 1, then we may consider the following simple formulation. So in the original paper of Wasserstein GANs, this is so-called Wasserstein weight clipping. So they clamp all the ways to a fixed box so that this phi here, so the only condition we need is phi is a Lipschitz function. So as long as the weight is small enough, then we can make it Lipschitz function. But the problem of this approach is this can overly restrict the class of functions. So then the next one is so-called WGP. So this is, I should say, works pretty well, and this is a nice model. But the problem is, as you see, so gradient of d phi, the norm of gradient d phi is not necessary to be 1 globally. So, and then another problem here is applying the gradient penalty at some sample points is not sufficient. So this is experimentally shown. So the main question is, how can we take this measure omega? So we have 2 measures, and then like there are actually many different approaches regarding this. We may consider the interpolation of mu and then the generated measure, and then we can also consider other interpolations. And another analytic and interesting work is the following recent work. So this problem, in fact, compute the minimum of a different optimal transport problem related to congested transport. So yeah. Then our question is following. So how to estimate the Wasserstein distance, and also as well as how to make algorithm perform well in the generative setting, and also how to enforce the Lipschitz constraint efficiently. So this is what I'm going to talk about today. I should also mention other like list of WGANs. So I think the first one is related to Simone's last question. So instead of the gradient penalty term, we may consider the maximum of 0 and then the following, the norm square minus 1. So, and there is actually like the second work, in addition to gradient penalty term, we can add some kind of Lipschitz norm so that Lipschitz constant is forced well. But the problem here is still we need gradient penalty term. And another work by Anton and also Guido and Augusto here. So we can also use Kontrabicci duality formulation, WGAN based on C transform. And this method allows for a more accurate estimation of the true Wasserstein distance. But as discussed before, it does not perform well in the general setting. And this is exactly the same figure that is shown in the last slide of Augusto's talk. All right, so let me introduce our comparison-based training algorithm. So I will explain 2 simple but important just ideas. So let us recall the original formulation of W1 distance. And as you may notice, like the maximizer of this, so the Kontrabicci potential phi can actually take any values at the complement of support of U union with support of nu, as long as phi is Lipschitz. So that means instead of the Lipschitz condition, we may consider the following observable condition. So instead of whole domain, it is enough to consider the support of mu times the support of nu. So it is actually clear that if both support are equal to omega, then this condition is equivalent to one Lipschitz condition, but which rarely happens in real world data. And also, using this instead of the original Lipschitz condition is more efficient if the support of mu and support nu is, let's say, they are small enough. And then what happens instead of the original Lipschitz condition, but using this previous condition, or doing some condition A, we can actually see that if as long as we have this condition, we can use the duality relation so that the one we compute here is also essentially one Wasserstein distance. Okay, so this is first idea. So this is again, maybe I should say simple and also well-known, but this will help us to compute the Wasserstein distance as well as train WGANs. And the second idea is also related to like training Wasserstein GANs. So in practice, one does not have access to the true distribution. Instead, when we compute the C transform, we can only consider a set of points. So like here, when we compute the C transform of phi, we may only consider the infimum over X in the support of mu n, and here mu n is an empirical measure. So this approach actually widely used in literature. But in fact, this C transform on a smaller set, let's say on the support of one measure, which is different from the original one. So the difference is just in the C transform on the support of eta, we take infimum over X in the support of eta, and then in the original C transform, we take infimum over the whole domain omega. So using these two ideas, so instead of Lipschitz condition, we use the Odumsov condition A, and then instead of also the original C transform, this is actually not easy to compute. So instead of that, we only consider the C transform on mini batches. Okay, and there are differences between the original C transform and then C transform mini batch. So maybe the main difference is if phi is Lipschitz function, then in the original C transform, phi C is for sure minus phi. And also we have the following dual deformulation. However, this relation does not hold in general. And as a consequence, phi C is not necessarily equal to minus phi, even if phi is a Lipschitz function. And this is actually the main idea of our algorithm. Okay, then what happens if we consider instead of the original C transform and the C transform mini batch? So consider two empirical measures. Now we consider the summation, the average of n delta measures. And then these are all our objective function. And it is clear that if our phi satisfies the Odumsov condition A, then we do have the following relation. So minus phi is less than or equal to phi C. Then also that means it is clear that we can compare J1, J2, J3, and J4 as follows, because it is enough to compare. For instance, when we compare J1 and J2, it is enough to compare minus phi and phi C. And equivalently, so this above lemma means that equivalently, if J1 is greater than J2 or J1 is greater than J3, then phi does not satisfy the condition. And similarly, if J1 is less than or equal to J2 for all empirical measures, then phi satisfies the Odumsov property A. So the comparison between J1, J2, so let's say J1 is less than or equal to J2 is equivalent to the Odumsov condition. All right, so here is our algorithm. So we would like to solve the following problem. So here, I just use any measures, not like neural network, but we'd like to solve the following problem. So infimum over all new probability measure, and then the supremum over this measure is, I should say, like J1 in our case. So our objective functions are here. And then we want to restrict phi to satisfy the Odumsov condition. So the idea is following. So since we want J1 is always less than or equal to J2, and then J1 is always less than or equal to J3. And then we know that our phi satisfies the Odinson property. So
nu being equal to mu be the minimizer.
So yeah, mu is a given measure, and then you like to find nu. So like in theory, mu, since we solve like the one here is the Wasserstein distance between mu and nu. So in fact, if nu is mu, then the one here is 0. But since mu is parameterized by like neural network, so yeah, this like this.
The true nature of the problem is not clear from the formula on top.
You mean like, so we want to minimize the Wasserstein distance, so that is the main object. And then here, what I did is we slightly like change the Odinson condition. So instead of the one machinist, we consider phi satisfies the condition A. Does this answer it?
But wouldn't it be true that if phi satisfies condition A, then minus phi also satisfies it, right?
This is slightly different, but yeah, yes, I think if you are saying that if nu is like nu is mu, then this part is 0, and that is true. Or
wouldn't that be the minimizer then?
the minimizer of this problem, or
Is
Oh, the one on top, right?
mu inside P omega.
yeah. So the support of mu is contained in omega.
Maybe because nu is the parameterized, so it's not the new of the mu. It's
Oh, okay.
theta of this guy
Yeah,
here.
yeah.
So you don't know. You want to find the best theta.
Right.
So
Thanks for the comment. So yes, the original problem is actually, we cannot just find nu, but we need to find some generator G, and then we want to find G. So nu need to be replaced by G push for some noise measure like rho.
Using a more restricted class than on P.
Yes, right, exactly. Any other question? Okay, yeah, thanks a lot for the comment. Okay, so let's go back to the algorithm then. So the inequality we need is J1 is less than or equal to J2. So if this inequality does not is not satisfied, then we want to increase J2. So that's why I use Adam here. And in fact, I just wrote for simplicity maximize J2, but more precisely, this increases J2 so that J1 is less than or equal to J2. And we do similar jobs here. And then if we have the right inequalities, then we maximize J1. So this is exactly solving the first problem. And then lastly, we need to also again minimize J1 with respect to the theta. So yeah, sorry, here I didn't include the parameter and then neural network here, but in fact, phi here is parameterized by theta. And then this is one neural network. And then here, V is also parameterized by theta, which is another network, more precisely. Nu is G push forward rho. Okay. Then I will introduce some experiment here so that, so here I consider two mixtures of 4 Gaussians. So you can see the yellow points and then also green points. So the country pitch potential phi can be computed as follows. So this here, this figure shows the values of country reach potential as well as the level set, you see that this is symmetry. So you can easily check that the optimal map from, let's say, one green point to yellow point is perpendicular to the level set here. And like, for instance, like W1GP, so state transform, we have actually a similar figure. So this method also has made the Wasserstein distance well. So, and then if we use other algorithms, then you can see that this has not accurate counter-reach potential. And this is our loss function as well as J1, J2, J3, and J4. So we have total of 5 functions, J4, W, J3, J2, J1. And you see that if we train the Wasserstein GANs, then this whole like quantities converges. And interesting part here is also W1GP with gradient penalty, it stabilized, but you see that this actually doesn't converge, and this is somehow expected because the Lipschitz constant is not in fact 1. And if we add more restrictive condition, lambda is 10, then these quantities are closer than the previous one. And what about the state transform? In the state transform here, like if I understand correctly, then we only use J2. So that means J2 actually converges well, but we have actually small gaps between other quantities. And another interesting part here is what happens, we only consider a small number of points. So we solved the exactly same problem, but with mini batches 8, mini batch size 8. So we use the 2,000 mixtures. And then you can see that in our algorithm, we can also have compute the counter-reach potential accurately. And also we can also compare the norm of d phi. So here, if the color is white, then it means the norm of d phi is close to 1. And maybe another like point is the point here, like the vertical axis, like x-axis. So this is in fact where phi is not differentiable. So we can also capture this. All right, and this actually works through in high dimensional data. So we sample 5,000 images of digit 1 and then also 5,000 images of digit 2. And then this also like converges. So all quantities converge as well. And so actually this result is similar to the ones with synthetic 2-dimensional data. Okay, so this was our first task. And the second one is, second task is perform well in the generative setting. So from left to right, the training data was MNIST and then fashion MNIST and CFR10. So you see that visually the generated images are of similar quantity, but our algorithm actually runs faster than this algorithm because we don't need to compute the gradient phi. So yeah, in fact, it is hard to find which one is good and which one is bad. So there is one measure which is called FID metric. So this is, I cannot say that this is like maybe effort or measure to quantify the quality of images, but this is just the square Wasserstein metric between two multidimensional Gaussian distributions. So when we compute this distance, we use the mean and also variance of distributions. So, and this is standard metric in this framework. And you see that like our algorithm as well as W1GP also converges to 0 well, and also they are actually really similar. And the last thing I was actually very interested in is we would like to enforce the Lipschitz constraint. And this is done by computing the following. So the supreme of the Lipschitz constant. And you see that in WGP, in fact, the Lipschitz constant is much less than 1. And also we do have some oscillation, but it is like between, like, let's say 1.5 and then also like 2.5. So these are experimental result. And so how many minutes? Okay. So then let me just give you maybe one remark, which is also related to previous figure here. So recall the state transform method. So this is similar. The left one is using J2 as objective function. And this problem, you see that has the following blurry images. And I would like to understand this more. So let me just interchange the supremum and then expectation. Then we will get one Wasserstein distance. And the question is whether an optimal mu is similar to the given property mu. And in fact, this problem, in fact, calculate the empirical distance, empirical Wasserstein distance between two empirical measures. So in fact, one can check that the answer is no, as illustrated in the following lemma. So like, for instance, when we consider a very simple case, so we consider one point as a mini batch, and then we also consider like one-dimensional data, then one can check that this can be, the median can be a global minimizer of the problem. So this is like, theoretically speaking, also related to the k-means clustering. So in fact, this state transform method probably compute or like probably similar to k-means clustering. So then what happens here is instead of the original problem, if we add the Wasserstein, the empirical Wasserstein distance, then probably we may control the centrality. So if epsilon is 0, that I presented earlier. So in this problem, our images are sharp. And then if we use, instead of J1, so this is an objective function, if we use J2 and J3, then we have blurry images. So that means we can, if we choose appropriate epsilon, then we can control the centrality, or let's say the blurriness of images. So that's one point. And like another point is actually WGANs with the two Wasserstein distance. So this actually has many advantages in theoretical perspective as well as applications. However, so there are like not many works in this respect. So if we can compute, if we can use the two Wasserstein distance, then maybe we can compute the optimal map. And also we may use this as one tool to compare with the Wasserstein gradient flow. So this is also like another like direction I'm interested in. So in summary, our algorithm infers one Wasserstein bound, and then without the need of introducing the gradient penalty. So that's our main goal today. And consequently, we don't need to worry about the parameter. So we still need to worry about the structure of neural networks, but we don't need to worry about the parameter in front of the penalty term. And also, this algorithm generate realistic images as well in many like these types of data. So yeah, thank you for your attention.
Thank you. Any question?
I may have just missed this, but how do you evaluate the sequence form in your training?
Yeah, so
Yes, that's actually good one.
So as I discussed earlier in this slide. Yeah. So here what happens is this new n is the summation of n delta functions. And so that means instead of infimum, it is enough to choose the minimum over this xi's. So this is how I compute
Okay,
the
so
state transform.
you evaluate this for every xi and just pick the one.
Correct.
So you do this with batch or with
Yeah, mini batch.
with batch.
Mhm.
And do you observe like a lot of oscillations going on if you choose a very small batch size?
You mean after we change?
Yeah,
So-
because in principle, this C transform has to be evaluated over the whole data set.
Right.
If you just use a batch, it's really biased. I mean, there's an induced bias there.
Yeah, so
Or
yes,
discrete.
yes, that's a good point. And then that's why in our experimental result, there are some oscillations.
Okay.
And then in fact, so if we can compute the original C transform, then maybe we can use that to train the network. But here the main problem is since it is not easy to compute the C transform. So instead we use this quantity, and then this is, since we are working on like many different mini batches, then eventually this can enforce the condition we need. So
Yeah, but you still have bias. It's not like a, I mean, normally when you do batch, the reason you can do batch is because it's unbiased, unbiased estimation. But because you have an infimum over there, automatically it's biased. So and no matter how many batch you use, eventually you would have bias for sure.
yeah, yes. Yeah. So like maybe in our reason. So it also, yeah, like for that reason, so it depends on our, let's say, the time step. So yeah, we do have oscillation. So that is exactly how I compute based on the state transform mini batch. So we do have oscillation. That's true. And then this oscillation becomes larger if the step size is bigger.
Okay, okay, thanks.
One more question.
I have to say I'm at loss at some of the things, but maybe this is related to this slide. How do you evaluate the kind of performance in the end? Because if okay, you only have sample digits, let's say, and if I had a mapping that precisely maps, I have a neural network which is over-parameterized that can represent anything. And let's say I map my initial distribution, maybe it's a Gaussian mu, exactly just the sample points. So now, whenever I want to draw something, I perfectly draw already one of the sample points. And if I measure what is the Wasserstein distance, it's going to be very, very small, right? So how do you kind of evaluate whether we have done well? Whether this is generating something that is out of the sample, because I guess collapsing to the sample is not what is desired. Thanks.
Yeah, so yeah, that is actually, I think, a very great point. So when you just estimate the Wasserstein metric, and then let's say that two measures are like far from each other, then we can have like this kind of figure in our data. However, while training WGANs, these two measures eventually converges. So, I mean, that's I hope. And so this can also measure for the quality of our synthetic images. But in fact, we need to see if our measure is close to zero. However, in fact, that's actually not easy question, I think. So in our experiment, our loss function like J1 converges. I mean, it is actually not easy to say because it goes to zero, but I cannot say that this is actually zero. So in this sense, I think this visual inspection is one way, but
But with visual inspection, I have no way of knowing if these points are already in the sample. I mean, I don't have a visual kind of understanding of such big data set, right?
So yeah, I should say that. So your question is, if the loss function converges to 0, then can you say that our algorithm works well or not? Or
well, I would say if it goes to 0, that means that what you're generating are already sample points, right?
Yes, yeah. But the problem is, first of all, so it is hard to compare with other previous algorithm because, for instance, in WGP, that algorithm actually don't compute the one Wasserstein distance. So our algorithm, the loss function goes to 0, but it is actually still clear if this means our images has good quality or not.
Yeah, maybe we can discuss.
Yeah.
Right. I'm really kind of, I see that GANs are, doing something well, but I don't quite understand what. So thanks.
Okay.
Yeah, there are some part of the.
You're not getting the last question.
You like very nice talks, right? Like the method and the lemmas, because we can very well.
But did you, like, when you do the comparison with the WGP, I guess it's the previous slide. So are you using the same set of hyperparameters of the WGP paper?
Yes. So except the lambda parameters, so
of course,
that we don't need that. And then also, in fact, in our algorithm, so in WGP, we need to, so the number of iterations is slightly different because we don't actually need more iterations. So that's different, but other parameters are same. Yeah.
So the tradition is that he get the last question.
Apparently. Okay. So my question was related actually to the C transform that you compute with the mini batches. So do you think that in some way, so because when you start from any phi and you just do the C transform on the whole support, you do like 3 times and then you stop and then that's it, right? Because it's in evolution.
Yeah.
But if you do it, with the Synchron algorithm, then it reaches to the optimal. Now, this seems to me in somewhat a noisy version of the C transform. Could it be that it works in some way when doing iteratively, changing batches and maybe enlarging the batches, you are converging in somewhat to the minimum?
Yeah, so
maximum.
That's actually what I'm also curious. So our algorithm, in some sense, can be also understood as the regularization. So and one of regularization is the Synchron algorithm. So in that sense, so maybe okay, so let me first say maybe one practical advantage, and then also I'm curious if we repeat this algorithm and then find the optimal contribution potential, then can we somehow show the convergence? So that's one thing. And another thing I should say is in this area, at least in the let's say estimating the Wasserstein distance, since we can compare like objective functions, so that actually makes us easy to choose appropriate like parameters. So I think that is one advantage of our algorithm, but this also can be understood as one of the regularization method to train WGANs.
So I suggest we stop here. So thank you again.
Okay. So thank you very much to everyone.